So we're going to plug in the 3 because we know this side has to either be above or below. So 3, negative 3 squared would be 9, minus 3 minus 2 would end up being 3 over 4. So at 3, we're at 3/4, which means this entire piece is above. Now, the middle piece is a little trickier because it could come down, hit that point, and go back up. It could come down, go through that point, and then just keep going down. It could come up, go through that point, or it could come up and go back down. So I'm going to have to see what it's doing between here and here, as well as there and there, because there is no guarantee that the whole thing is above or the whole thing is below. So the easy one to plug in between 0 and 2, I would plug in a 1. So 1 over negative 2, so that's there. But now I got to plug in something between 0 and negative 1, and it doesn't really matter, but probably the easiest thing to do would be negative half. So if I plug in negative 1/2, what is negative 1/2 times negative 1/2? 1/4 minus negative 1/2 minus 2. If I make all of those have a denominator of 8, that's 1/4 plus 2/4 minus, I think I said 8 when I meant 4, 8/4. So 3/4 minus 8/4 is minus 5/4. So the minus over the minus is going to become a plus. So that tells me it's going up. Remember, to divide fractions, we multiply by its reciprocal. So 8/4, which is 2/5. So about there. And really, the dots are not as important as the direction, just knowing that that arrow needs to go up and that arrow needs to go down. So, this is going to be the piece that you tend to struggle the most with because it's not really apparent. It's not something that repeats. Each one is different, and you have to just continue to apply the things you've got to worry about. Where are my asymptotes? Where does it cross the x-axis? Where does it cross the y-axis? And then where are those pieces? So now, based on that graph, what would my range be? All real numbers. My graph would be all real numbers. Okay? All right. So we're going to do one of these every day because this is where you need the practice. Okay? This is where you're going to need the practice. All right. Let's go back to our 12 basic functions. I'm going to go through some of them a little quicker today. I don't really remember, had we just talked about building the parent points here? Okay. So remember I picked these because they were nice perfect squares, but this square root could just as easily become 4th root or 6th root. And then I would want to pick numbers that, like 1 times 1 times 1 is 1. 2, 2, 2, 4 times would be 16. 3, 4 times would be 81. Okay? And so we did discuss that you won't always have to scale by ones. You scale what makes it more appropriate for a given graph. Okay? But the point being, this has to be positive. And that ties back to that conversation we had a minute ago about these different roots. And as long as it's just that x under there, then whatever's under that radical has to be greater than or equal to 0. Okay? All right. Now I'm going to look at some of these out of order because I want to address them really quickly. Find the one on your paper that says sine function. All right, this one I am not going to expect you to be able to draw. If I gave you this picture, I would expect that you could tell me the domain of this is what? All real numbers. The range of this is what? -1 to +1. And that it is bounded. Agreed? Why do we say bounded? Because it's bounded above and bounded below. Odd, even, or neither. It's odd, right? Couldn't I turn it on this number right here 180 degrees and then right back up with the same graph? So I am not going to ask you to draw that. There will be a whole unit on sine, and you will eventually draw that, but it is not going to be drawn on this first test. But if I put that picture in front of you, I expect you to be able to tell me those things from that picture, okay? Same thing with cosine. Domain. -infinity to infinity. Is range still -1 to 1? Is it still bounded? Odd, even, or neither? That one's even, because this reflection, correct, just over the y. So that one is even. Now, in your homework tonight, it's going to refer back to these, but you don't have to have them memorized. Just look back in your notes to answer the homework questions, okay? Find the one that says the logistic function. Domain. All real numbers. Range. Parentheses or brackets? Because these are serving more as what? Asymptotes. Is it still bounded? Odd, even, or neither? Neither. That one would be neither. And so really that's all I'm worried about, just learning to recognize them. But these are not ones you've talked about, so when they become important, we'll spend a lot more time on them. Okay? So now let's go back. Oh, wait, let's deal with one more. The greatest integer function. Notice it says the function has jump discontinuity. Remember talking about jump discontinuity, removable discontinuity, non-removable discontinuity. It's removable when it just has one little hole in it. It's non-removable when it has the asymptotes. Okay? So when we get, well, in a minute we'll look at the one that has the non-removable discontinuity. And when you have the different stages, we call it jump. All the greatest integer function does is round everything down to an integer. Round everything down to an integer. So if I am between 0 and 1, it's going to be 0. If I am anywhere between 1 and 2, it's going to be 1. Anywhere between 2 and 3 is going to be 2. It just rounds it down. So the only thing you have are your integers. This is the one that gets tricky to y'all because y'all think you're going up when you're really going down, because remember -2 is really littler than -1, but y'all tend to think you're getting bigger because you're saying -2 instead of -1. So when I am in here, you go down, you go to the integer below it. The greatest integer function takes it to the integer below it. So what is the integer below 3.7? 3. What is the integer below -1.6? -2. So you go to the integer below it. And that is what the greatest integer function does. What would the domain of that be? All real numbers. What would the range of that be? It's just the integers. And we would not be able to write that in interval notation because there's no way in interval notation to list every integer. Okay? I mean, I can go, because if I go 1 to 2, that means everything between the 1 and the 2. So there's no way to list just the integers in interval notation. All right, going back to something that hopefully is familiar, absolute value function. It's a what? V. What's the domain? What's the range? And this one works a lot like x squared. Is it okay? Oh, bounded above, below, or neither? This one would be bounded below. Odd, even, or neither? Even, because you can reflect over the y-axis. So, because the domain is all real numbers, is it perfectly okay to choose -2, -1, 0, 1, 2 for my parent points? And what is the absolute value? 2, 1, 1, 2. And then this would do what to those parent points? Left 3. This would do what to those parent points? Up 7. This would do what to those parent points? Vertically stretch, right? This would do what to those parent points? Horizontally compressed. Because remember, the 2 is read as a half. The 2 is read as half. So it's going to pull it in, which is going to make it skinnier. So that one should be one you're fairly comfortable with. Should recognize what it looks like, be able to easily recognize that one. All right, let's go to reciprocal function. All right, so what can x not be? 0. So my domain is -infinity to 0, 0 to infinity. Range. Same thing. The degree at the top is smaller, correct? Which makes it y equals 0. Can 1 over x equal 0 over 1? No, because 0 would need to equal 1, and it can't. So my range is also -infinity to 0. All right. Bound it above, bound it below, bound it or not bound it? Not bound it, because that just keeps going up and that just keeps going down. Odd or even. Flip over the y, which makes it even. Rotate about the origin, which makes it odd. So which one is it? Odd. Okay. Now, this is not one that I would choose to graph using parent points. So see if y'all vaguely remember doing something like this. So your asymptote was at 0, your asymptote was at 0, and this is the corner 1, 1, and this is the corner -1, -1, and we just kind of threw them in those corners. Okay? So if I give you 1 over x plus 2, what is that going to do? So we just moved this asymptote left 2. We left this asymptote at 0. And then we pretended this was the origin. And then that point became 1, 1 and -1, -1. So we're not going to build a whole big set of parent points. We're just going to move our asymptotes left and right and just worry about those. And I really could care less if you even put the dots there. It's just getting them in the appropriate corners. Okay? So left and right is going to change which asymptote? the vertical, and up and down is going to change the horizontal. Now, do not confuse this with this. This is not a transformation of this. This is a beast all of its own. There is no transformations. There is no parent points. It's just looking for all of the pieces. This is only appropriate when you have x to the first power. There's no x's on the top. Okay? And so these are a whole other situation. They do not tie back as a transformation of that. Okay? All right. Exponential. Anybody remember exponential? Domain. All real numbers. Range. So, do include the 0 or exclude the 0? Exclude the 0. This has a horizontal asymptote at y equals 0. It would be bounded below, odd, even, or neither. Neither. Is it okay for me to let my x be -2, -1, 0, 1, and 2? All right, so I'm going to do this function first. If f of x equals 2 to the x, make it easy. What is 2 to the second power? 4. 2 to the first power? 2 to the 0 power? 1. And then if that was 2, then this was 1/2. And if that was 4, this was 1/4. Remember those tables? And if I change it to 3, these become 9s and those become 3s. And if I change it to 4s, those become 16s and these become 4s. All right? So that's the easy table. And then if I do 2 to the x plus 1, I'm going to take all of those points and move them what? Left 1. So if I shove this whole graph left 1, is my domain and range still the same? Yes. But if I do 2 to the x plus 1, then that's going to shove all of those points up 1. So if I do that, did I just change the asymptote and the range? Okay, the asymptote and the range. Now, the problem is they're referencing e to the x. And remember, e is 2.7 blah, 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 blah. Okay? So I would know that e to the 0 power is 1 and e to the first power was 2.7, and beyond that I would have no clue if I didn't pick up a calculator. All right? So I'm more concerned that you have this general understanding of the shape and understanding where the asymptote should be. So what affects that asymptote? Up and down. As long as you understand to level it at the 1 or level it at the 2, and you can just draw that in there, that's my big concern at this point. Okay? And recognizing that that's an exponential graph. Now, natural log. Remember, exponential and log are what of each other? Inverses. So what did we do to build our log? We let y be what? -2, -1, 0, 1, and 2. And then if I did log base 2, because of the nature of log, didn't that mean 2 to the y power equaled x? So you're doing the same thing, 2 to that power, but you're building it upside down. So 2 to the second power is 4, 2, 1. So what would go here? 1/2 and 1/4. You're just flipping those around. But that also means you flip the who? Domain and range. So now my domain is bigger than 0. My range is, which means then it is not bounded because there's no restriction on the range, correct? Odd, even, or neither? Neither. Okay. Who's going to affect this time it's a vertical asymptote, so what's going to affect that? Moving it left and right or moving it up? So as long as I move this thing up and down, does it still to the right of 0? But once I start moving it left and right, do I change this asymptote, which is then in turn going to change my domain? So you're worried about that left and right. And again, I am not worried about a beautiful graph. Just understand that exponential does that while log does that. Remember, ln means log base e. ln means log base e. Okay? All right, so what I want y'all to do tonight is, if you'll continue, I want you just to look through all these examples that are in this packet. Just read through them. It's just going to reiterate the bounded, the symmetries, the things that we have already talked about, okay? And then, not quick review. Make sure you get to the actual exercises. And in the exercises, I want you to do 1 through 28. Now, understand, I'm not asking you to graph 28 things. You are matching right here. And then, these other questions, don't look at these pictures. Look back at your parent functions. So, which parent functions are bounded? Which parent functions are not bounded? Just things of that nature. You're just answering the questions in terms of the parent functions, not these pictures. Not these pictures. So you're really physically not graphing anything. You're just answering questions about the graphs. Okay? All right. I didn't collect those papers from y'all, did I? Let me grab those really quick.